we have gender, we have information on race and on income. So they're real and they interact with their environment, but they're not actual persons that can be identified. So that's a good way of kind of expressing what we're talking about here. So, we'll be talking first about some concepts of what they are. Then we'll look at how we construct a U.S. synthetic population. We have done some of this work for other countries as well. I'm not covering that in this session, but I'd be happy to answer questions about it. We'll spend a little time looking at the geography of synthetic populations and how the aspects of these data, which are point location data, differ from polygon data, which is normally how we look at sociodemographic data. And then we'll look at some applications that we've put synthetic populations to use in. So first of all, what is a synthetic population? It's a computer representation of households and individuals that reflect the statistics, geography, and behavior of real populations. So we have developed this U.S. data set that includes data on households and data on people, and we know which people are in which household, and then we have characteristics of both. So synthetic population is microdata, which means that we have a record for each of the entities in our data set. Normally with census data, we're dealing with aggregated data. So if you have a map of the U.S. by county or by census tract or by zip code, you're displaying aggregated data, counts or rates and that sort of thing by a geographic area. Here we have individual records, so that's why we call it microdata. So we can, in our case, we've created a synthetic population of people and households, but you can really think of a microdata set and a synthetic population representing any particular entity. So people have used it to represent animals, in the case of chickens or poultry, for dynamic simulation of poultry disease. Malaria has been modeled in this way, where actually even every particular mosquito has been represented in the data set. So you can do a lot of different synthetic populations representing different things, but we'll stick to humans for the rest of this session here. So why do we have to do this? Why create a synthetic population? Why don't we have the population already? Don't we have all the census data? And the problem with the existing census data that most of us are familiar with is that it isn't a very good source of data for use in agent-based models, which are models where we're actually having every single person and or household interact with each other and with the environment. And so if we have aggregated data, it doesn't work well in that kind of model. So we don't really have a list of every household and person in the U.S. that has their sociodemographic characteristics. It doesn't really exist. So this quote here by Balas, I think, represents the reasons really well. If we don't have a microdatabase on individuals and households, then we have to simulate one. So that's what we try to do here. So probably the first and primary reason for creating synthetic populations is to serve as agents in agent-based models. So as I mentioned, these are models where we simulate the interactions between agents, or in this case people, and their environment. And one of the classic kinds of models that these are used for is what are called SEIR models. This stands for susceptible, exposed, infected, and recovered, which is kind of the standard model used for infectious disease like influenza. So an SEIR model takes a population, and some of the people are susceptible to disease, some are not. So for example, they might already have had the disease, so they have developed an immunity. Some people are exposed. Some people who are exposed become infected, and after a while, some people who are infected recover. So we use SEIR models to simulate a outbreak, a pandemic, and we can use the model as an experiment to look at different ways of handling the outbreak. So we can simulate what would happen if we close close schools for a certain amount of time? Or what if we have a vaccine and we distribute that to everybody, or we distribute it to half the people, or we distribute it to healthcare workers? That's the idea of targeting vaccination. So it's like a way of experimenting on a societal level without actually having to infect people with influenza. We can see how it might, its course might go depending on the interventions we want to study. So I have a brief video here that just shows an example of an influenza model that we developed. This shows the state of Pennsylvania, and I'm going to play it twice. The first time through, you just get an idea of what it looks like. And I'm going to describe what you're seeing here. The yellow dots, each dot is a block group. So we've already had to aggregate our synthetic population from the household person level up to block groups because there'd just be too many to map at a household level. And then as the simulation goes on, the yellow dots represent the percent of people infected. And they rise up out of the screen and they turn from yellow to orange to red, the higher the percent of infected people is. And so we can see how this particular epidemic spreads across the state of Pennsylvania. So these models are spatial and temporal, and they allow us to see how an infectious disease outbreak might occur, especially under various conditions that we might want to test. So what does the data look like that we're talking about here? Fundamentally, you can really think of it as two tables in your database, a household table and a persons table. And I've highlighted a single dot on the map, which is a household, and it has one record associated with it in the database. It has an XY location, and it has demographic or social characteristics of that household. There's 4 persons in it. The age of the head of household, or the householder as it's known now, is 47. The household income is $55,000, and there's 2 vehicles on this house. Our data that we're using now actually would have race as that 4th characteristic there. And then the household has 4 persons, so there's 4 records in the persons table, and they're linked to the household by the ID. And this linkage is very important for certain kinds of models, especially infectious disease models, because transmission within a household tends to be higher for diseases like influenza because there's more contact between people in a household. So we have to maintain that relationship, and that's an important aspect of a household person synthetic population. So for each person, we also have characteristics, age, gender. Some of the things we do in addition to the standard variables are we assign children to schools and we assign adults to workplaces. And there's a whole slew of additional characteristics of those persons as well that come from census data. But this is the essential concept or characteristics of the data itself. So let's talk about how we get to that point. Our primary source for the U.S. data is what's called the American Community Survey, or the ACS. This replaced the old census long form that used to be done every 10 years. This is now a survey that is ongoing all the time throughout the year and is run by the Census Bureau. And this collects similar data to the old long form. So it collects information about your home, what kind of heating fuel you use, how many rooms, what you pay in rent, all kinds of characteristics about your household. And then for each person in your household, when you fill in this form, you describe each person, how old they are, their gender, what their occupation is, what their educational attainment is, and so on, a whole variety of things. Roughly, I believe throughout the year, about 1 in every 15 households will get this survey each year. And then the census uses this to create 2 products. One is counts by unit of geography, so standard census data that says how many people live in Raleigh, how many people live in Wake County, what's the proportion of people living in households and not households by tract or zip code or whatever. And a lot of that data is available in a site called the American Fact Finder site that the Census Bureau runs. The other kind of data is what's called the public use microdata samples, or PUMS data, and that is another key source of data. So we use both the count data and we use the microdata sample from the ACS. So the summary data would look like this for a variable such as household income. Because this is a numeric variable, they make ranges for their summary. So in a particular area, let's call it a block group, there's 9 households that have an income less than 10,000. There's 21 households that have an income from 10 to 15, and so on. So we're counting households based on this range of income variables. So that's the standard aggregated data. And then the microdata looks like this. It's individual records that are culled right out of those ACS forms. So we have both records for households and we have records for persons. It's de-identified, so there's no information in here about the name or address of persons. It does have location, but only at the level of what's called a public micro-use area, which has roughly 100,000 people in it. So these records are associated with those areas, but they're fairly large and there's a fair amount of people in them, again, so it's difficult to re-identify any of these particular records. So the tricky part is that we have to be able to figure out how many households to make in each block group so that we have the correct proportion of households of certain household age and certain races and certain incomes and certain sizes. And so I'm not going to go into a lot of detail here, but the issue is that we may have a variable, in this case it's the number of workers in the household, and we have over here we have the count of how many households have 0 workers. Well, there's none in this block group. There's 121 households that have 1 worker and so on. So we have these counts of workers in the household, and we also have counts of the age of the household down here. But we don't know how they interact together. So we don't know how many households have 1 worker in them and the age of head of householder is 45 to 54. So we use a process called IPF, iterative proportional fitting, a standard statistical method to estimate the proportions of households that have 1 worker and a 45 to 50-year-old head of household. And so we fill in these proportions so we know which public use micro records to pull to completely construct the 100% population for the block group. Now, we use 4 variables to try to match all together to get the best set. If we use more than 4 variables, then it gets more and more difficult to get a good match, because for each of these variables, income, age, household size, which is the number of occupants, and race, we're trying to count up and get the right number of households for a particular income category for all the different age categories and all the different sizes and all the different races. So we're trying to construct the resulting data so that we have the right number of dots, and the dots represent all of these different characteristics at a summary level, at the block group level. So summary data, which is the ACS counts by block group, the 5% microdata, which is the actual records we use. We actually replicate those records, but we select them to match the summary data. We use this iterative proportional fitting, and we create the 100% microdata synthesized from those 2 sources. So it's not completely accurate. It is not, we don't have a source of all of the records, so we have to simulate it. We have to do our best to select the right records to match what the census aggregated data counts are. And remember, the ACS data and all this data has margin of error around it. The ACS summary statistics are actually have quite wide margins of error. So even if the Census Bureau says there are 15 households with a certain income range, there's a margin of error around that count of 15. It might be anywhere from, they might think it's anywhere from 5 households to 30 households, but they say it's 15 is their estimate. So, okay, so we get this list of households and persons, and then we have, we want to put them on the ground. We want to figure out where they are. So we know which block group they're in, which is the yellow boundary here, because all of the ACS data, the aggregated data, we know the block group identifier, and we know all the characteristics of the aggregated data for that block group. And then we select from the microdata to create this list of households for a particular block group. And then we put them, these red dots, on the map. And we do that based on a high-res population density layer, which is shown in the blue shaded squares here. And so the data set we use for that is something called the ICLUS, which is the Integrated Climate Land Use Scenario data set from EPA, so it's an open data set. And so it has counts of people or households by each of these 30-minute tiles. These tiles are 30-meter tiles. So where there's a higher density identified in the gridded data, we put more households there. Where there's no households, like the shopping mall over here, where it says no households, we don't put any dots. So instead of just randomly locating all the dots within a block group, we use this high-res population density to put the dots where households actually are. Most of the time, we do have some none of this data is perfect, and so sometimes we have households in streets and in parking lots and things like that, but it's still better than a random location. So we do all that. We do it for every state, we do it for every county and block group in the U.S., and we wind up with something like this. So I don't know how many of you can pass the geography test, but this is the LA County area in Southern California. And the viewer that is has the URL down at the bottom of the screen, synthpopviewer.rti.org, these graphics come right from that website. So you can use that website to explore anywhere in the country. You can zoom and pan anywhere. Actually, I'm going to go ahead and bring it up here. Here's the viewer. And you can just click and drag, and you can see any of the 4 variables. This is income. You can turn on a black background if you'd like. You can also use what's called quad view, where you can see all 4 variables at one time. And so this viewer is just a handy way to get an idea of what the data looks like. And it also is actually quite fascinating. I've spent many hours looking at different cities throughout the U.S. In this way, just to see how they vary. It's really quite interesting. Okay, so we got all these dots, and even though this looks color-coded, it's actually dots on the map here. And so we have household color-coded by household size, household income. Blues are higher income, yellows are lower income. Notice that in LA County, a lot of the blues are along the coast and the edge. I thought that was kind of interesting. And the yellows are more in the interior. Household or race. In just about any major city in the U.S., you see extremely significant heterogeneity in race. And so LA is actually not as bad as many others. The kind of turquoise color is African American, purple is Asian, and the orangey red color is whites. And then household or age is the 4th variable. It's very interesting to look around and see where there are elderly neighborhoods, because they pop out in magenta. And you can also, if you look at New York City and Manhattan, if you look at the household size map, which is the upper left one here, it is almost entirely blue, because there's more than half of the households in LA have 1 or 2 occupants. Interesting. Now, how well do we do in matching the synthetic data to the actual household counts in the census? Well, here's one example. This is for the count of 3-person households by block group. So each dot here is a block group in North Carolina. And on the x-axis is the observed, in other words, what the ACS thinks there is for each block group in terms of the count of 3-person households. And on the y-axis is what we get in the synthetic population. So there are minor differences. We don't get quite the exact count we should get when we try to do this for all the different categories we're looking at, but it's a pretty close match. And then if we look at geographically, the reds and oranges here are where we have created more synthetic population households than compared to ACS, and then the blues are where it went the other way. There's more in the ACS. But there's no block groups in the whole state where the difference is greater than 6.6%. And then if you aggregate up to tracts, which is what we're showing here, there's even fewer big differences, and then at the county level, there's even smaller differences. Okay, let me switch now to some of the geographic issues, and I call this the tyranny of polygons. We're all used to seeing maps by polygon. This is block groups in Baltimore. These are arbitrary. They're made by the Census Bureau. They don't really aren't done to reflect the reality. And so we are all used to seeing maps color-coded by these types of geography. So here's just a straight count of total population by block group. Sometimes it's better to show it as a density. So this is the density of people per square mile. So count divided by area. We get a completely different looking map than the population map. And then we could also look at other things such as crime. This is a crime rate map, so it's a count of crime divided by the number of people in the block group. So rates are frequently shown for diseases and things like that. One of the things that's very misleading about this map, and any map that has shaded geographies, is you get things like this one. And I hope you can see my mouse on the screen. But there's this very large dark brown polygon just to the south of the harbor. That's got a very high crime rate. The reason it's misleading is that there's hardly anybody who lives there. So one way we can alleviate that issue is to do what's called a cartogram, which is what's shown here. And what this does is it warps the polygons so that their size is relative to the total population. So this is a more realistic, even though it's a little more difficult to tell what's what in Baltimore. But that same area just south of the harbor that was a big, huge polygon in the previous map here gets really small because there's only maybe 10 or 12 people who live there. It's a very industrial area. So we really should take into account the area of the piece of geography when we're doing choropleth maps like this, but few people do that. And this all gets into the ways that a map maker can portray data in a way that tells the story they want to tell. And there's a book about this called How to Lie with Maps, which is a takeoff on the How to Lie with Statistics book, but it's the same idea. You can make a map to show any story you want to. The other issue with polygon data is the modifiable area unit problem that geographers are familiar with. So if I have data on persons or households, and I aggregate it up to some level of geography, the boundaries I choose will show a completely different result, or the result would be different depending on the boundaries I choose. So this quote saying the aerial units are the zonal objects, in other words, tracts or zip codes, used in many geographical studies are arbitrary, modifiable, and subject to the whims and fancies of whoever is doing or did the aggregating. So an example is of block groups. Here's the percent black population in Baltimore, and this vertical line is just a major street that divides many of the block groups here. There's no kind of left and right part of this particular graphic. But these are just arbitrary polygons, and the percents are therefore based on those arbitrary areas. So let's take an example just to show you what can be done with this issue of modifiable area units. Here's a bunch of white dots and red dots that are scattered across the landscape. Let's say these are actual households. And if we draw 4 boxes and we count up the percent of red dots versus white dots in each one, we get 5% white dots in the upper right, and in the upper left it's 80% white dots. What if we were to draw the boxes like this? It's the same dots, but now our boxes are kind of horizontally oriented and we get a different percentage. Now what if we draw the boxes vertically? We get a different percent. So depending on how we draw the boundaries, we get different results, and that's the modifiable area unit problem. There's no real great solution to that issue in geography, but one of the things that we like about synthetic populations and having the dots is if you don't have the dots, what is the truth? So if we've got the dots, we can make maps like this. So these are the locations of our synthetic households, color-coded by race in this case. So you can see both density, you can see color-coded based on the variable, which is the race of the householder, and you can see a lot more of the fact that the map is blank in many areas where nobody lives. If you recall the maps of crime or of total population earlier, everything had a color, and so this shows areas where no people live. So this is a very nice way to use the data. And I can draw any arbitrary polygon I want on here and summarize the data underneath. So let's talk briefly, and I know I'm running short on time, so I'm probably going to skip a couple things, but let's say we wanted to add on to our synthetic population a characteristic from another source, in this case the National Health and Nutrition Examination Survey. They have a variable called food insecurity, which is a code from 1 to 4. 1 means you're highly food secure. In other words, you have enough money and access to food to feed your family and yourself. And to a food insecurity value of 4, which means you are highly food insecure. You may not have enough food to feed your family, or you might run out of money by the end of the month and not have enough to purchase food. So we want to add that characteristic, which is this code from 1 to 4, to every person. And so we do that by taking the NHANES data and we calculate a probability of a person having a code of 1 through 4 based on their demographic characteristics, their gender, their race and ethnicity, the number of occupants in the home, their income, and their educational attainment. And so we use these probabilities and we go through the entire synthetic population and we roll the dice, and 74% of the time a person with these characteristics will be highly food secure because they, in this case, they have relatively high income, high educational attainment, and so on. So we can use this method to attach additional characteristics to the synthetic population. So I've mapped here the high food insecurity households in an area, and then I did some cluster analysis to create a map showing where there are high food insecurity areas, and then map the clusters. So that's a way of adding behaviors to the synthetic population. Same example here, looking at smoking risk. So we have demographics about what kinds of people smoke or are more likely to smoke. Attach those characteristics to the synthetic population, and we can make a smoking risk map. Blue is low risk, red is high risk. Or obesity. So blue is low risk of obesity, reds and oranges are higher risk of obesity, again based on demographics and another survey. Another thing that we might want to do is use the synthetic population in, so I'm getting into some of the applications. This is a video that shows what would happen with sea level rise in eastern North Carolina. The yellows are the inundated areas over the next 100 years, and the charts show how many people by various characteristics and how many businesses would be lost or forced to move based on that particular sea level rise scenario. I'm just going to show it real fast here again. Because we got dots for both the businesses and the synthetic household, it's really easy to make these sorts of summaries and analysis, assuming we have a good sea level rise model. Okay, and another kind of application is emergency management. There's a circle on this map, maybe a little hard to see. It's a 10-mile radius around the Sharon-Harris nuclear power plants right in the middle of this map. And there's, across the U.S., every nuclear power plant has a 10-mile evacuation zone, where if there's a certain level of accident, there may be a requirement for everybody within that 10 miles to evacuate. And so this shows the use of the synthetic population as black dots here to illustrate what might be facing the emergency management people. So, and I've just got a couple of statistics here to help this out here. So there's 19,705 households in the 10 miles. There's a lot. 52,000 people. But one of the interesting things that emergency management wants to do is they want to know, for example, I mean, most of these people have cars, they can get out. Well, who are the vulnerable people who cannot really move easily? Well, we use the synthetic population to query the data and say, how many of these households are single-person households? There's 3,800 of those. How many of those have the occupant being 64 years or older? Well, there's 942. Of those, how many do not have a car? 171. So that gives the emergency management preparedness people some idea of the magnitude of the issue they'll face, because they're going to have to find these people and help them get out of this area. Now, on this map, I could show those 171 households as dots, but we don't really know exactly where they are in here because of the uncertainty in the placement of dots in block groups and things like that. But it does give a good piece of information for emergency management. Another application that we have used the synthetic population for is mass vaccinations. And the issue here is that a county such as LA County, they have 205 locations where they can do mass vaccination. So if there's a really bioterror outbreak or anthrax or smallpox or something really crazy, and they need to vaccinate everybody very quickly, they need to choose the best places to do those, to provide those vaccinations, where people drive and go there and get a vaccination. Now, we're not taking into account the fact that the freeways would be totally flooded in an event like this, and LA County didn't really care about that either. But what we did is we took a genetic algorithm. Underlying this is the synthetic population, so all 6 or 8 million people in LA County, and we analyzed every combination, or a large number of the combinations of 7 sites out of the 205 sites available, and picked the best 7 to minimize overall travel distance for the population. And so I'm going to show a quick video of this. And each time this algorithm ran, it would calculate. Now it may not come up here. I know I'm running short of time, so I think I'll go ahead and skip this. I'm going to go on. But ultimately, the point is that we can use the synthetic population to do a better job of assessing distance and time and things like that in emergency scenarios. And finally, another application is environmental risk. So in this case, we created estimated plumes of groundwater contamination around gas stations throughout the U.S. I think we had about 40,000 gas stations. And we created these plumes depending on different amounts of releases from underground storage tanks and the duration of the release. And then, so we have that color-coded plume with the risk, and then we can overlay the synthetic population, the households, and the yellow dots, and we can very easily calculate a risk for each household, summarize it by each gas station or across the country to have a better estimate of risk. So that's another application. And I will close there. Whirlwind tour through. I wanted to leave some time for questions, and so I'll close there. Thanks.
Thank you, Bill. Thank you, Bill. We have a couple questions from the audience here, and I'm just going to read those, and you can address them.
Okay.
This question is, have any of these techniques been applied outside of the U.S.? The speaker says, or the questionnaire says, I work in developing countries where there is a strong desire for these types of analyses. Without the richness of census data, are these approaches feasible?
We have done several synthetic populations in other countries, but the quality of the results really depends on that census data availability. So in many places, the data is not very rich, and there's just not much more we can do in the synthetic population. But some countries provide a microdata sample, just like in the U.S. I mentioned that PUMS data. Well, many countries do provide that PUMS data from their own censuses. And so for those countries, we can do a pretty good job of generating a synthetic population with some richness to the characteristics. But in any case, no matter where in the world you're doing this, you're not going to have the geographic specificity that we had in the U.S. one, where we were showing very small geographic areas, block groups, which can be extremely small. We have data, summary data for each block group. For any of these international censuses, even the ones that have the microdata samples, the geographic coding is either at the province or the district, which would be similar to a county level. So we can generate the synthetic population, and it's fairly accurate based on that data, but we can't do a very good mapping in a precise way to show the difference from one village to another village. We just don't have that level of data to be able to do that. So it varies a lot. We can do it to a better extent in countries that have microdata. In countries that don't have microdata and they just have kind of aggregated distributional data, we can do something, but the geographic scale in any case will not be as good as we get in the U.S.
Okay, another question. What is the source of the sea level rise data? For example, is it based on actual water elevation?
Yeah, I'm embarrassed to say that's not really a sea level rise model. I think people call that what we did a bathtub model. The point was not to do a nice model of sea level rise in this case. So all we did was we took the projection for sea level rise in North Carolina at 2100, and we just divided that equally up into the years from 2010 to 2100. So that was the amount of rise that would occur each year, and we simply selected the elevation grid cells that would be below that sea level value at each year. So it's not really a model that we stand beside. It's really just stand behind. It's really just it was used as an illustration to show how if you had a nice high quality model of inundation, just overlaying the dots on top of that would really provide an easy way of making estimates of the demographic or business impact.
Okay, a third question. If I understand the basics of the process, you created the synthetic population based on 4 basic characteristics of the original data. You indicated adding more dimensions was problematic. Is there a scenario where it would make sense to generate the synthetic population based on a different set of characteristics depending on the phenomena you are investigating?
Yes, absolutely. So those 4 variables we chose for our generic U.S. data set, we thought were probably those that would be of most interest to the most number of applications, or most appropriate for the most applications. But there may be cases where you don't really care much about, let's say, income, but you do care about whether we have the correct proportion of owners versus renters. And so that's a different variable. And so we do have a system which will allow us to create a customized synthetic population where you can select a different set of variables to, in other words, tune the synthetic population. So, so yes, that is possible, and it is certainly something that is important to certain applications where there are other variables that are really important to have, very accurately portrayed than the ones we have chosen just for the generic one. So the answer is yes. Now, not every variable that's in the ACS can be used because there has to be a similar kind of variable in the public use microdata. And also, I would make the point that all of the selection of the households based on the ACS data, I would highlight that those are household characteristics. So we're not matching on people, we're matching on households. So when we have matched on age of householder, we're using that as a proxy to get a fairly good distribution of age in the persons. But when we select a household from the microdata, and that household had a 57-year-old who filled out the form. If we select that household, we get the people who are in that household, the actual people. And so it's not a direct matching of household, of person-level age when we do the selection. But if we get the right number of households that have people greater than age 75, the head of household are greater than age 75, then we're going to have a pretty good likelihood of having those households probably not with young children in them, and probably even not too many middle-aged people, unless there's, you know, a grandparent-parent kind of thing going on. So it is all households, and so the person-level characteristics kind of come along, and they're pretty good, but they're not explicitly matched to the census data.
Okay, we don't have any more questions that people have typed in. I do have a comment, Bill, from one of our researchers here, Brian Blanton, who asked the sea level rise question, saying that it could be very interesting combining our FEMA-funded sea level rise impact study for North Carolina with your population model. So maybe that's something you guys can connect on your own.
Absolutely, that'd be fun.
Sure. Are there any other questions from the audience? And if not,
I would make one other point real quickly, if I can, that since we have a few minutes, I didn't describe another system we have that sits on top of the synthetic population that's called FPOP. And just really quickly, what it does is it allows us to take this baseline population and age it forward into the future. And it takes into account fertility, mortality, family, household formation, and migration. And so that may be of interest to some people in the audience who are looking at, in the case of climate change and sea level rise, it takes a long time for that to happen. And the population 50 or 80 or 100 years from now looks different than it does today. And so we have a way of taking that into account and simulating a future population that may have different characteristics than today's population. So just a quick mention of that other tool.
Yeah, that's really cool. Thanks, Bill. I guess that will wrap it up for today. Thank you, Bill, so much for taking time to present this information. It's very interesting, and we appreciate your time. For those of you in the audience, remember that DataBytes is a monthly series, and our next session will be Wednesday, May 6th, same time, noon. We're going to try once again to do our Internet of Everything webinar that got canceled in March, so mark your calendars. Once again, Bill Wheaton of RTI, thank you so much, and thanks to everyone in the audience.
Thanks for all for joining. I appreciate it.
Okay, great. Have a good day, everybody.
Hey, bye-bye.
Bye-bye.